Welcome to this explainer. Today, we are going to break down the conceptual scaffolding of distributions and descriptive statistics. So let's start with a classic engineer's dilemma. Imagine you are tasked with assessing the heights of a massive coastal seawall network. Or say you need to evaluate air quality across a sprawling, congested city. You literally don't have the time or the budget to go out and read every single sensor in that physical system. So what's the workaround? You take a sample. But getting that sample is really just half the battle. Now you actually have to make sense of it. And just a quick aside before we get fully into the weeds here, the underlying concepts we're talking about today, they work identically whether you use R or Python. Because this is entirely language agnostic, we aren't going to look at any actual code syntax today. We are focusing strictly on the ideas. Okay, so take any numeric vector of those sensor samples. Let's say it's a list of 100 seawall heights. That list is actually a distribution just waiting to be seen. If you stack those values in order and then count how often each range occurs, well, you've just drawn a histogram. And if you go ahead and smooth out those blocky bars, you've sketched your density curve. Stroke by stroke, a simple, flat list of numbers transforms into a tangible geometric shape. Now, every single distribution you'll ever encounter shares 4 fundamental traits. First, size, which is just how many values you actually have. Next is location, telling you where the bulk of the data is clumped together. Then spread, indicating how much those values vary from one another. And finally, shape, which describes the overall geometric outline of that curve. And that brings us to the actual definition of a statistic. Honestly, there is no magic here. A statistic is quite literally just one single number, summarizing one of those specific traits of a sample. That's it. It exists purely to help you make a concrete engineering choice when you're faced with uncertainty. To really wrap our heads around that trait of spread, I like to use the analogy of a spread ladder. We climb it step by step. The first rung is the standard deviation, and that simply averages the distance of your values from the mean. The second rung is variance, which actually squares that distance. Up on the third rung, we have the coefficient of variation, which drops the units entirely. And finally, the standard error, which adjusts for the size of your sample. Let's look a little closer at that step from the first to the second rung. To get there, we have to look at deviations, which is literally how far each individual seawall height strays from the mean. Variance squares those deviations, and by squaring them, it heavily mathematically penalizes extreme outliers. It makes those unusually tall or dangerously short seawalls absolutely impossible to ignore. So why do we need those final 2 rungs of the ladder? Well, the coefficient of variation drops your units entirely, whether that's meters or parts per million, so that you can compare the spread of totally unlike systems. It's a real game changer for comparative analysis. The standard error, on the other hand, adjusts for your specific sample size. It gives you a uniform measure of variation, meaning you can compare a tiny sample of seawalls in one town with a massive sprawling sample of infrastructure in another. All right, we've got spread down. What about shape? We break shape into 2 distinct concepts, skewness and kurtosis. Now, both of these are built from the exact same mathematical ingredient we just talked about, deviations from the center. Skewness simply asks, which side does the bulk of the data sit on? Kurtosis, meanwhile, asks how tightly bound that data is around the center. Are we looking at a sharp, pronounced spike or a wide, flat mound? Once you know your shape, you can start comparing it to named distributions. These are basically archetypal shapes generated from just 1 or 2 statistics. Think of your classic normal bell curve, a skewed Poisson, or an exponential decay. We take these simulated, perfectly clean archetypes, and we lay them right over our messy, real-world data to see which one it actually resembles. And right here is the critical mistake that so many people make. Do not, under any circumstances, treat descriptive statistics as mere administrative bookkeeping. They are absolutely not just mathematical chores you check off before you get to the real analysis. Instead, think of descriptive statistics as diagnostic gates. These numbers are what decide which archetypal distribution your data plausibly came from, and that resemblance strictly dictates what engineering methods and models you are mathematically allowed to use at all. As you do this work, you've got to constantly contrast your results. A sensible result? That's when your expected archetype neatly fits your smooth data. But a suspicious result, say, finding heavy, dangerous tails being hidden by a blind, overly simplistic average, well, that requires you to immediately stop, investigate your reference axes, and thoroughly check your control limits. So before you ever apply a complex model to your data, you must ask yourself one question. Does the raw geometry of this data actually permit the method I am about to use? Because if you don't know the shape of your system, you don't know your system at all.